Hello everyone, and thank you all for joining us in this, which is the fifth of the 2017 series of webinars which discusses LimitState products, their features and their applications. I'm Tom Pritchard, I'm the host for today's session, and I'll be introducing our speakers shortly and rounding up at the end of the webinar. Today's webinar is entitled Modelling Soil Reinforcement with LimitState GEO, and it should provide you with an overview of the software's engineered element material and how it can be applied to a wide range of soil reinforcement problem types, such as soil nails and geotextiles. The main part of the webinar will run until about 1:15 UK time and have a few minutes at the end for questions. You can post these at any time via the question functionality that should be present in the webinar interface in front of you. We do try to answer as many of the questions as we can in the time available, but because it's quite a short webinar today, it's not always possible, but we will try to reply to questions that we don't cover during the webinar itself over the preceding few days. So I'd like to introduce you today to our speaker, who is Dr. Colin Smith, and he is the LimitState GEO Product Manager.
Okay, thank you very much, Tom. So good morning to those of you in the European time zone. Good afternoon or evening to those of you joining us from elsewhere in the world. As Tom has stated, my aim today is to show you how LimitState GEO can be used to solve reinforced soil problems, how it differs from other methods, and how to model a number of specific scenarios. To this end, I'll be using a mix of slides and the software to illustrate the key points. As this is a problem-specific webinar, I'm going to focus on how to use the software to solve soil reinforcement problems, and so therefore may skip over some of the basic details of how to use the software, but the process should be clear. So I think it's useful first to give some context to the software and to the company LimitState. University of Sheffield has been conducting research into limit state analysis and design and the use of optimization in civil engineering for almost 2 decades now. The company was spun out from the University of Sheffield in 2006 with the aim of making this research available to industry and providing easy-to-use, powerful software tools that are well validated and supported. The company has 3 civil engineering products at present: LimitState Ring, LimitState GEO and LimitState Slab, with several more in the pipeline. And these are used by consultants and contractors, large and small, in over 30 countries worldwide. And as you may be aware, LimitState GEO is a general-purpose ultimate limit state software, able to determine the collapse state for any problem geometry, and able to model slopes, retaining walls, structural elements and soil reinforcement, as is shown by some of these examples. So our aim today is to focus on soil reinforcement analysis. So, quick introduction to soil reinforcement. As I'm sure many of you are aware, reinforcement works primarily by adding a tensile strength to the soil, or equivalently transmitting load from one part of the soil body to another. And reinforcement may be one-dimensional or two-dimensional, so it can include soil nails, steel strips, geogrids, geotextiles, etc. And there's a large number of applications for soil reinforcement, and I've given 3 examples here as modeled by the software. So a soil nailed slope, a reinforced soil wall, and a reinforced embankment on soft ground. Now, in terms of analysis, if we look at standard textbooks and design codes, we can see a broad consensus on the general principles of modeling reinforcement. Either the reinforcement pulls out of the soil or the soil moves past the reinforcement, but essentially the relative interaction is the same and can be modeled in a fully general way. Now, for example, slope analysis, one can use the method of slices as illustrated here. The presence of reinforcements allows additional stabilizing forces to be applied to each slice, and determining these pull-out forces is one key element to the analysis, and these can be determined differently by different analysis methods and software. But before we cover that in more detail, let's look at how LimitState GEO itself works. To set the software in context of currently available software, then on the one hand we have software based on conventional approaches, such as a method of slices, which do a pretty good job specifically for slope problems. It's up in the top left-hand corner here. And for more complex analyses, finite element software is available which can model pretty much any problem geometry and complex soil behavior. But it typically requires quite a lot more expertise to use. And there's a gap between these, and we feel filling that gap is computational limit analysis. It provides the geometry flexibility of finite elements with the ease of use and simplicity of traditional methods. Essentially, the only parameters you need are cohesion, friction, and unit weight. And this is what the LimitState GEO software provides. And we can take the same type of approach to other engineering applications, say in arch bridges with the software LimitState Ring, or in U-line analysis of concrete slabs with LimitState Slab. Now, underpinning all these methods is a key enabling technology, discontinuity layout optimization. And it's useful just to quickly recap on how this works. So if we look down at the bottom left-hand side of the diagram, we have a very simple problem here. It's a rectangular block of soil with a surface load and supported on the left-hand side and on the base. What we do in DLO is we don't employ elements as in the finite element method. It's what's called a node-based method. So we populate the domain with a number of nodes. Here we're just using 12 nodes. And we connect every node to every other node with a potential slip line. So if we have 12 nodes, we effectively have 12 times 11 over 2, 66 potential slip lines. And that can be formulated as a linear optimization problem to find the critical collapse mechanism for those particular boundary conditions. And when we solve that, we end up with this mechanism, essentially constructed out of 6 of those originally 66 slip lines, and we can get the collapse load and the failure mechanism in that process. Now that's a simple example. It's just use 12 nodes. Typically when we're solving problems with the software, we'll be working with 500, 1,000, 2,000, 4,000 nodes and a correspondingly huge number of potential slip lines. So the more nodes you put in, the more accurate the result, because the more slip lines the software can consider in terms of generating the optimal mechanism. But typically it can solve those problems in a matter of seconds very interactively. Now, in terms of soil reinforcement, we can capture several modes of reinforcement failure interaction with special reinforcing elements in the software, which I'll explain in more detail in a moment. So in terms of modeling the reinforcement in this problem, we can see that we have an issue. We've got multiple wedges of soil that are sliding. In some cases, soil may be moving relative to the reinforcement, or the reinforcement may be moving relative to the soil, pulling out from it. But it is possible to model this in a fully general way, addressing the whole range of failure modes. Essentially, all we need to do is define the pull-out force per unit length for that reinforcement. So as you can see in this slide, we have different relative movements between the soil and reinforcement here. At this end you can see the reinforcement is pulling out from the soil, and in this case we've actually modeled the case where the reinforcement is pulling out of the wall element if we didn't make that connection strong enough. So all those kind of elements can be modeled. Now before we go and look at the reinforcement in more detail, the method has been verified against a wide range of closed-form solutions and benchmarks. Every time the software is modified, we run well over 1,000 tests to make sure that the software does what it's supposed to do. And we've put over 100 of those up on the website that you can download and view. This just shows one example of soil reinforcement comparing the DLO analysis with some work by Lashinsky in 1987, and we get a pretty good match across there. Software has also been used by quite a number of authors to look at a range of problems, including reinforced soil. You can download from our website a bibliography listing all those papers. This is just a sort of snapshot of the page for reinforced soils. Okay, so that's a kind of general introduction. We'll now look in detail at how the software deals with reinforcement. So we're going to first look at soil nails, or one-dimensional reinforcements. The software can model one-dimensional and two-dimensional reinforcement with slightly different tweaks to the parameters. So just a recap on how we expect a one-dimensional element to operate. For an undrained soil, if the nail is pulling out of the soil or the soil is moving past the nail, then we assume that we get a shear force along the nail where the shear stress is alpha Cu. And for a cylindrical reinforcement such as a soil nail, the pull-out force is simply going to be the circumference of the nail multiplied by the shear stress per unit length of nail. For a drained soil, we would approximate the shear stress at failure on the nail as being alpha times the normal stress, effective stress, times tan phi dashed, perhaps, and again we can multiply by the circumference of the nail to give us an overall pull-out force per unit length of nail. And because the LimitState GEO software is essentially two-dimensional, these must be specified per unit width into the diagram, so effectively taking account of how many nails per unit width into the diagram you have. And essentially these two quantities, the first part of this quantity in red here and the first part of this green equation, these are constants which we can feed into the software to allow it to model the interaction between a one-dimensional element and the soil. So we'll just show you how that works in the software itself. So I'll just bring up the software here. So this is the software, and I'm going to open a predetermined example, which is this one. And this essentially shows we've got a rigid block here with a piece of reinforcement embedded in it firmly, and another piece of reinforcement along here embedded in a block of soil, and we're going to just pull that out and see what happens. So a very simple sort of element test. Now before we go on and discuss that in more detail, we'll just run through a little overview of the software. You'll see the screen is laid out. The problem geometry is obviously in the middle there. We have a number of buttons along the top row and the left-hand side. We also have what's called the property editor on the right. So anything you click on in the software, its properties are displayed here. So currently the properties displayed are the general overall project properties. We also have what's called a materials explorer here, which allows you to quickly create new materials and look at properties of materials. And down here with a geometry editor, which allows you to modify the geometry. So if I click here on the soil, you'll see that the properties of this block appear, and it says inside this block is a material called the soft clay, and the parameter we're interested in here is its undrained shear strength, which is 30 in this case. We also can look at the engineered element itself. So this reinforcement element is here. This is made of what we call an engineered element in the software. It's called R2 here, and I've set that for a pull-out factor of 10, a pull-out strength of 10. And that corresponds to a nail that's approximately 10 centimeters in diameter, spaced at 1 meter intervals into the diagram, embedded in that clay soil of shear strength 30 kPa, assuming full adhesion. We'll look at these other parameters a little bit later on. So the other thing we're interested in is the length of that nail. So its geometry appears down here, and it runs from 2 to 4 meters in the X direction. So it's basically a 2 meter long nail, and it's going to be pulled out of that soil. So what we expect is to pull that out if it's got a pull-out factor of 10 kilonewtons per meter squared per unit length, and it's 2 meters long. It should pull out with a force of 20. So if I click solve here, the software effectively determines the load applied here required to cause failure or pull out. So it's a very simple problem to solve, and that's the result. We pull the software out. The result is 20 as we expected, and this software will also give you a little graph of the axial force in this case along the nail, and as you'd expect, starts off at 20 here and fades to 0 at the far end. Now I can undo that. I can also look at the properties of the nail. I can click on it here, but I can also click on it here. I know it's made of material R2, so clicking on here also brings up the same properties. And what I can do is double the pull-out force, so that's either me doubling its diameter, or I could be putting in the same diameter nail but twice as densely, so 2 every meter into the diagram. And then if I solve that again, as we would expect, the pull-out force doubles to 40. Fairly straightforward. Now I'll set that to 100. We might expect the result to come out as 200, but actually we get a result of 120, which may seem a little odd at first sight, but if we think about it, that's fairly logical. Effectively, if we've put in a pull-out strength of 100, and that's trying to represent a row of nails, essentially we're putting our original nail in at 10 centimeter spacing. Effectively, it's all those nails are kind of merging together and forming a planar reinforcement. And if we have planar reinforcement in a soil of strength, let me just unlock that, so just remind ourselves the soil is a strength of 30, then the pull-out on a planar sheet of reinforcement should be its length 2, multiplied by 2 to account for the top and bottom, multiplied by 30, which should give us 120. And that's exactly what we get here. So the software is doing the right thing. Finally, what I'll do is illustrate one other feature here. We have the rupture strength here, so that's basically the tensile strength of the reinforcement. Currently we've set it to effectively infinity, 1E30. If I set that to 60, then it will fail in tension at a stress of 60, and if I solve that, you can see that now the collapse load has gone down to 60. It's modeling the stresses, axial stresses building up fairly linearly here, but they finish at 60 at this point. And you can see the reinforcement stays in the soil. If I press this animate button again, it's effectively just stretching ductile in a ductile way at this point in the analysis. So we can also model tensile failure of the reinforcement as well as the interaction of the reinforcement with the soil. Okay, we'll jump back to the presentation briefly. Just pull that one up correctly. Yep, there we go. So we'll have a quick look at how we can use that nail model in a bigger problem. So we'll look at a soil nail slope. So this is based on a study published by Clark et al. In 2013. Putting in nails horizontally in this case, diameter 0.25, we've assumed full adhesion, horizontal nail spacing of 1, C dash for the soil of 3.5, phi dash of 26. So in the software, there are 2 parameters we would set called TC and TQ, and they basically account for the cohesive component of pull-out per unit length and the frictional value. So the TC is simply the circumference times alpha C dash divided by the spacing, which comes out at this value, and the frictional component is this one. And in the software basically takes that number and multiplies it by the nominal normal stress on the nail, or vertical stress at the level of the nail. There are further factors to convert vertical stress to all-round normal stress that are recommended in textbooks for different situations and could be included in the calculation of this number. But those are the 2 numbers that we're going to put into the model. So I'll jump back to the software and we'll open up that one. So that is effectively the model. If I click on the nail here, you can see the 2.744 and the 0.383 values here. These are the pull-out factors. We also have lateral factors, so these account for the amount of energy or the resistance of the nail to soil moving laterally past the nail. In a conventional analysis, those are normally ignored. And so if we want to emulate a conventional analysis, we'd normally set those to 0. In fact, we put a very small value in, because if we didn't, the nails could, in principle, float out of the soil if they wanted to. So that just stops that particular issue. So if I click solve on here, the software quickly identifies a critical failure mechanism, and in this case, if we just have simple nails in the soil, we get a very localized failure at the front of the slope, and just a little bit of shear resistance holding it back there, and we get what's called an adequacy factor of 1 here. Now what we've done in the software is the software has two modes of calculating collapse. One is factor load, where we take a load in the system and find out how much we have to increase it by to cause collapse. One is factor strength, where we take the strength of all the soil elements in the model and reduce those, or find a factor by which those must be reduced to cause collapse. For simplicity, I'm just working with factor strength in this one, where we're just applying the factor to the weight of the soil. So essentially, a number 1 here means we have to increase the weight of the soil by a factor of 1 to cause collapse, which means the system is essentially on the point of collapse. Now we can explore what happens if we change the length of the nails, what happens perhaps if I shorten them. We can do that simply by, we can modify it directly on the diagram. I can just pull these elements inwards just by clicking and dragging with a mouse. So I could say half the length. Rather than doing that there, I've got a model which I've already done that too. So that's this one here. And clearly, if we've got some very short nails in there, we don't expect them to do a great deal. And in fact, what the analysis is showing is that the slope failure is essentially just going around the outside of the nails and pretty much ignoring them. And here you can see our factor on load has gone down to 0.4, which means that this is definitely well beyond the point of collapse, and we have to actually reduce the soil weight or multiply it by 0.4 for it just to be stable. And so it's quite easy to explore changes in reinforcement strength, etc. on these types of problems. And if you click on these elements, the nail, we can actually look at the stresses in the nail. So as you'd expect, 0 at the ends and building up in the middle as the shearing goes through that. But in this case, there's not a lot of force being transmitted through the nail. So jump back to the presentation. Just to wrap that one up, this analysis has been compared against a classic two-wedge analysis, where effectively the software has been forced to do a two-wedge analysis, and then compared that with the classic sort of hand calculation. And as you can see from this graph, the software does generate exactly the same result as the hand calculation. But of course, if you don't restrict it, to force it to find only a two-wedge failure mechanism, allow it free to do that, then it will find a more critical mechanism than that particular case. So just to wrap up then with soil nails, we have a generic implementation of the software which allows soil to flow past the reinforcement, which allows us essentially to model a pseudo 3D case. We've got one-dimensional elements in it, what is essentially a two-dimensional analysis. It has been calibrated against a two-wedge analysis, and when we're using it with the software, we put in a pull-out coefficient, which we can either calculate or you might get from tests. You have the option to put in lateral resistances, but they're often set to 0 to be consistent with conventional analysis, and you can put in a rupture strength as well. And there is a facility to put in boundary materials above and below the element, which we'll look at in a moment in the context of planar reinforcement, but that is not necessary in this case if you've actually specified a pull-out resistance. So that's a quick look at soil nails. We'll now look at a second example, which is a reinforced embankment. So this is using two-dimensional planar reinforcement. And in terms of how that interaction goes, we would model that using the same, what we call engineered element in the software. We're going to model geotextile in this case. So we model it as a flexible element with zero bending strength, just allows it to bend freely. And the kind of interaction, again, we've got shear resistance top and bottom, whether the reinforcement or the geotextile is being pulled through the soil or the soil is moving past the geotextile. And the soil may move past at different rates above and below the geotextile, so we want to capture that kind of behavior. So in this case, we just directly specify the interface properties above and below the reinforcement. And that allows us to model differential shearing. Normal stresses will be determined inherently by the analysis, and those pull-out and lateral resistance parameters that we saw for the one-dimensional analysis are not used for the planar analysis. We simply set those to infinity, and that forces any failure to occur on the boundary interfaces. So just to illustrate that, we'll jump to the software again and look at a simple element test, which is this one. So again, this is very similar to the previous one, but if I click on here, we have an engineered element. The pull-out factor and lateral factor have been set effectively to infinity. We only need to set one of them, the TC or the TQ values, to infinity. So we set TC and NC to infinity, and then we're just going to pull that element out of the soil. Now the clay soil here, again, we've now got a strength of 50, and the length of the reinforcement runs from 2 to 3.5, so it's 1.5 long. So I'll click solve, and we would expect the pull-out force to be that 1.5 meters length of soil times 2 to account for the top and the bottom of the reinforcement times the undrained strength of the soil, which was 50. So that gives us 150 as we would expect, and that's the answer we get from the software. Again, we can see the tensile forces building up to 150 at that end. Now that's assuming full adhesion or full friction between the soil and the reinforcement. We can, however, add in interface properties to reduce that. So for illustrative purposes, we're going to use different values above and below. So we're going to put in a coefficient alpha of 0.9 above and 0.6 below. Now I've created materials here already to do that. So here I have an interface material that has 0.9 of the strength of its parent material, and the parent material has simply been set to be the clay, which is in the main body of the soil. So this feature in the software means that if you change the strength of the clay here, it's automatically followed by this interface material. So if I half that strength, then the interface material will also half its strength. It will always stay 0.9 times the parent material. So that's 0.9, and then this interface below material has an alpha of 0.6. So I can apply that in several ways. If I click on the element, you'll see I can put a material on the top and the bottom. So if I click here and click change, I can add what I want. So here I want the interface above, and then if I click on there again and click on the bottom one, I can select interface below. So now if we zoom in, you can see that those materials are actually shown there, and that will change the interaction. So if I solve the problem, what we're going to expect is that the new load should be the length of the reinforcement, which is 1.5, multiplied by the undrained strength of soil, which is 50, multiplied by the sum of those two alpha factors, 0.6 and 0.9. So it's basically 0.9 plus 0.6, which is 1.5 times 1.5 length times 50, and that gives you 112.5. The software's rounded that up, but anyway, it's 113, so that's the result we're expecting. So that's essentially how we'd use these elements. put interfaces materials above and below, and specify infinite values in these cases. So let's return to the presentation and look at an example. Oh, sorry, I missed one last bullet point here. We can also put tensile rupture strengths in for the reinforcement as for the nails. So we'll look at a reinforced embankment. So this is one sheet of reinforcement separating our embankment over a layer of soft soil. And the sort of questions you might ask are what kind of slope angles are feasible at the side? How strong should that embankment soil be? How high can we build the embankment? And what's the required rupture strength of the reinforcement? So we can model that kind of scenario in software. A traditional type approach might look at a kind of log spiral or a circular failure surface, depending on the nature of the soil type, and we could try and look at the stability there. But that's not going to be able to capture all failure modes, whereas the LimitState GEO software can do so. So we'll look at an example and just show you a few of those sort of failure modes. So I'll just open up the reinforced embankment example. So this example, we're just modeling half the embankment for simplicity. So we've got a line of symmetry down here. If we look at the soil properties, so if I click on here, it's basically been modeled as a sand with a small C dashed of a half, friction angle of 32, unit weight of 18. The soft soil down here is modeled as undrained strength of 16, unit weight of 15. And the geotextile itself, we've got these values all set to infinity, 0 moment of resistance, so it can be flexible, rupture strength of 25 in this particular case. And we've also got a top boundary and bottom boundary, which are giving me an alpha of 0.8 on both above and below the reinforcement, but they are tunes relative to the material that's above and below, so their parent materials are different. So if we solve that, and what I'm using here now is a factor strength mode. So what the software is going to do is find the factor we have to apply to the strength of the soils to get collapse. So what it's saying is that in order for the ultimate limit state to be attained here, or to get collapse, we have to divide the strength of the soils, that's of the sand and the clay, by 1.23 in order to get collapse. Otherwise it's stable. So any value here, adequacy factors here basically that are bigger than 1, whether we're doing a factor load or a factor strength analysis, mean that it's essentially not going to collapse, and we have to do something to the system to make it collapse, make it weaker, or increase a load. So we can see a sort of circular type of failure. We can see the reinforcement distorting, and if we look at the tensile force and the reinforcement, it's actually being taken to failure. It's taken up to its yield strength of 25 in this case. We've done some analyses against this. In fact, there's a paper out which looks at that. You can find it in the bibliography, but it's been checked against slip circle and method of slices methods. We get close agreement for this kind of failure. So that's a failure we get if the geotextile is pretty weak. If we up that to, say, 250, just for illustration, just click yes there, just check I've done that. Yeah, it's 250. If I then solve that again, because I've strengthened it, we're going to get a bigger adequacy factor. Comes out at 1.43, and in fact the system is now predicting that as we reduce the strength down by that factor, the first failure that's going to occur is actually a slope failure, and the reinforcement is building up to an axial force of 240, which is just below that 250. So we can capture a simple slope-only failure. Now, it may well be that we can look at what happens if we have a very, very weak soil underneath. I'll just reduce that to 8 just to demonstrate a different failure mode. So in this case, what we're modeling is effectively a squeezing mode where the embankment pretty well drops vertically, and squeezes or extrudes the clay out sideways, a classic sort of extrusion type mechanism here. So that's something that's quite difficult to get with a slip circle method, and so a slip circle would generally overestimate the capacity if that was the type of failure mode that occurred. And here our adequacy is just dropped below 1, therefore we would, this is not stable as it stands. I should add, of course, that we need to employ the right number of nodes in these analyses to get the accuracy that we require for the illustrative purposes. In this webinar, I'm using a fairly coarse set of nodes just to make sure the analyses run through quickly till we get the principles rather than the precision on the answers. We'll look at one other failure mode then. So if I revert that strength back to 16, so I should have unlocked it, and what I'm going to do is change the top. I'm going to make this almost a frictionless interface on the top boundary, so very low, and then what we'll see is that the software will find failure at the top, but it's finding a wider failure than it did before because it's capitalizing on that weak interface. So we get a somewhat wider failure mode and a lower overall fractal strength. So that hopefully illustrates the range of kind of failure modes that we can get with that approach. So it can pretty well pick up any failure mode. So if we jump back to the presentation, just to summarize that then, we have a generic implementation available in LimitState GEO for modeling planar reinforcement. It's been calibrated against method of slices and the slip circle analysis. And essentially, the recommended approach to modeling that 2D reinforcement such as geogrids using the engineered elements in the software is to set these pull-out and lateral coefficients to infinity. They are basically numbers that control one-dimensional reinforcement properties, so we don't need them for 2D. Put in the specified rupture strength and define your boundary materials above and below the element using appropriate interface factors, and set the bending strength to 0 if you're using a flexible geotextile or geogrid. So we're coming towards the end of the time allocated for this webinar, so we'll just wrap up with some conclusions. So to summarize, hopefully you can see that the reinforcement modeling that we use in the software uses the same essential mechanics as conventional methods, such as the two-wedge method, but it effectively allows thousands of wedges to be modeled if required. There's no need to separately consider internal or external failure, pull-out lengths, etc., reinforcement rupture. All of those are captured in one single analysis, so the software will always find the most critical failure mode, and any others that might occur will be less likely to occur. So we search all possible failure modes every time you solve, and we can model both one-dimensional and two-dimensional software reinforcement. Hopefully you've also seen, as I've been using the software, that it's a very interactive software. It solves quickly, so a lot of our customers use the software interactively to answer what-if type questions. It's very easy to change parameters and geometry, so it gives you a much better feel for a problem. And the one piece of software can solve any ULS problem type. So no need to put in idealizations or correction factors for non-standard geometries, and no need to learn how to use many different programs. So at this stage, we have a few minutes left. So I can take any questions if you have any, so you can type those in. To that. So let me just look at those. Okay, so question: when solving the problems, the white lines showing potential slip surface touch the boundaries. Does this mean do you need to extend the boundaries? Generally that is true. So if I put up the software here, and if I pull up one of the other models. Let's try the slope. In this case, the reinforcement doesn't touch the boundaries, but if the slip lines did touch a boundary out at one corner, generally that means your boundaries are too close. If they're just artificial boundaries, so this back boundary on the model here is artificial, we're not assuming that there's a wall of rock here. Essentially, we assume that normally you're going to have more soil of the same type behind. So yeah, if the boundaries touch, if the slip lines touch the boundary, that means you need to extend that. Okay. I've got a question about, is it possible to apply forces between geogrids and facing elements? I've actually got a model. This one's for soil nails, but you can actually model, here I've got something that's partially facing. So effectively what I've modeled here using the same engineered element is either facing or a nail head here. In fact, for simplicity, I've modeled this as essentially a two-dimensional strip going into the diagram, which these nails are connected to, and they will clearly provide more reinforcement to the soil. They're going to restrict soil flowing out past the nail. So if we solve that, we get a slightly different mechanism than if we didn't have the nail heads there. In fact, what it does is it pushes the mechanism backwards and increases the stability in this case. So it is possible to model these kind of connections, and again, it's just kind of inherent in the software how you set those up. Just a question, just reflecting back on those TC and TQ values. So as I mentioned, these values here, now when you click on any of these properties in the software, actually a little explanation is given down in this window here, and it also has a hyperlink to the manual. So if there's things you're not sure about, but essentially these numbers are only used to model one-dimensional reinforcement, such as soil nails. And generally, if you're following trying to match conventional type analysis, these two numbers are going to be set to 0 or very close to 0, the lateral factors. It's the pull-out forces you want, and they essentially represent the pull-out of one nail per unit length of nail per unit width into the diagram of the software. So it's those two values that were picked up. Those types of equations I showed on an earlier slide for calculating pull-out factor, you essentially would put those kind of numbers in for that particular problem. Unfortunately, we are just about out of time now, so what I'm going to do is pass back to my colleague Tom just to wrap up. So thank you very much for listening, and I hope you found that useful.
Thanks, Colin, and thanks again to everybody for joining us today. We do hope you found it informative, and as mentioned at the beginning of the webinar, if it's prompted any questions, then do get in touch with us. And ones obviously we've not answered here, do get in contact with us via support@limitstate.com, and we'll be happy to answer them for you. If you'd like to watch the webinar again, or if you think you know somebody who'd be interested to see it, there's going to be a recording available within the next day or so. There'll be an email sent out to you, so please just check and see if you get that. Also, please look out for event notifications for other webinars and events that we'll be sending out via email over the forthcoming months, or actually posting on our website at www.limitstate.com/events. Also, there'll be a quick questionnaire hopefully after this webinar finishes on your screen, basically just to ask how you found out about the webinar. If you're able to answer that, then we would very much appreciate it. So finally, I'd just like to say thank you all again for listening, and I hope you can join us again for one of our future sessions. Goodbye.